and welcome. Today, we're going to dive deep into something that's like the bedrock of all physics, Sir Isaac Newton's three laws of motion. And look, these aren't just some dusty old rules in a textbook. They are the principles that literally connect everything, from a tiny pebble on the ground to the planet swirling through space. So, let's start with the big question that started it all. What in the world could a falling apple and the orbiting moon possibly have in common? I mean, think about it. They seem totally different, right? One plummets straight to the ground, and the other just hangs up there, endlessly circling us. What's the connection? And the guy who cracked this massive puzzle? None other than Isaac Newton. His idea was absolutely revolutionary for the time. He said that the very same force pulling that apple to the ground was also the force holding the moon in its orbit. He created one set of rules to rule them all. Okay, so to really get what Newton was talking about, we've got to learn to speak his language. And it's a language that's built on just a few really powerful ideas. These are the building blocks for his three famous laws.
All right, first up, force. It sounds simple, and it is, but honestly, it's everything in physics. A force is just a push or a pull. That's it. It's the thing that causes any change in motion. It can speed things up, slow things down, or make them change direction.
Okay, next up, we've got mass. This is really just how much stuff makes up an object. It's super important because it's the measure of how much an object resists being moved, which, as we're about to see, is a huge deal. And that resistance to being moved, well, it has a name: inertia. It's basically an object's lazy streak. It just wants to keep doing whatever it's already doing. If it's still, it wants to stay still. If it's moving, it wants to keep moving just like that, forever. You know, this whole idea of inertia is so important, so fundamental, that Newton gave it its very own law. This is where we get into his first law of motion.
So the law basically says things are going to keep on keeping on. A golf ball sitting on a tee isn't going anywhere until you hit it. A spaceship drifting through deep space will drift in a straight line forever. But here's the kicker, the most important word in the whole thing: unless. Nothing changes unless an outside force jumps in and messes things up.
And this isn't just abstract physics, right? This has life or death consequences. Just think about a car crash for a second. The car is moving, and then a wall, the outside force, brings it to a sudden, violent stop. But guess what? You are also an object in motion. Your body's inertia wants to keep flying forward right through the windshield. That's why the seatbelt is there, to be that outside force that stops you safely. Okay, let's put this idea to the test. Let's do a little thought experiment. Picture a hockey puck just gliding across perfectly smooth, totally frictionless ice. It's moving along at a nice 3.37 meters per second. Now, if there are absolutely no other forces acting on it, what do you think its speed will be about 4 seconds later? And the answer is, you guessed it, exactly the same, 3.37 meters per second. Because there's no outside force, its inertia just keeps it cruising at the same speed and in the same direction. It's so simple, but when you think about it, it's incredibly profound.
Okay, so law number one tells us what happens when there's no force. But what happens when there is a force? That's the job of the second law. It gives us the actual math to figure out what's going to happen.
And that brings us to maybe the most famous equation in all of physics, F equals ma. Force equals mass times acceleration. This little formula is the key that unlocks exactly how an object's motion is going to change. And remember, acceleration isn't just flooring the gas pedal, it's any change in velocity, speeding up, slowing down, even just turning a corner. This table breaks it down perfectly. The relationship is pretty straightforward. If you increase the force, you increase the acceleration. Think about a shopping cart. The harder you push it, more force, the faster it accelerates. Simple. But for mass, it's the other way around. If you increase the mass, the acceleration goes down. It's way harder to get a cart full of groceries moving than an empty one, right? Same push, less acceleration. All right, let's crunch some numbers. Say we've got a block with a mass of 28.2 kilograms, and we give it a shove with 52 newtons of force. How much does it accelerate? So if F equals ma, we can just shuffle that around to find the acceleration. A equals F divided by m. We plug in our numbers, 52 newtons divided by 28.2 kilograms, and we get 1.8 meters per second squared. The math just works. So we've talked about objects all by themselves and what happens when a force hits them. But here's the thing. Forces never happen in a vacuum. They're always an interaction, a dance between two objects. And that brings us to the third law, the rule for every single interaction. I'm pretty sure you've all heard this one before. For every action, there's an equal and opposite reaction. The two words to really lock onto here are equal and opposite. It means forces always, always, always come in pairs. You literally cannot push on a wall without the wall pushing back on you with the exact same amount of force. And this isn't just for pushing on walls. This happens on a cosmic scale. The sun's gravity is pulling on the Earth, right? That's the action that keeps us in orbit. But at the exact same time, the Earth's gravity is pulling back on the sun. That's the reaction. The forces are perfectly balanced, an identical cosmic handshake. Okay, and this is where it all clicks into place. This is the grand finale. Newton took his 3 laws of motion, combined them with this idea of gravity, and finally answered that big question about the apple and the moon. Newton's big leap was realizing that gravity isn't just some local Earth thing. It's the universal outside force that runs the whole show. It's what holds us on the ground, what makes the moon orbit the Earth, what makes the Earth orbit the sun. It's this incredible action at a distance that connects everything in the universe.
Okay, I know what you're thinking. The full-on equation for gravity can look a little scary, but don't worry, we can use a really cool trick called the ones method to get our heads around it. We just pretend our starting force is 1. Easy enough. Now, say we want to see what happens if we double one of the masses. We just swap out that variable for a 2, and the result, the new force, is 2. It doubled. Now, what if we double the distance? Since distance is squared in the equation, the new force is 1 over 2 squared, which is 1/4. The force gets 4 times weak.
Okay, you ready for a little quiz? Let's use this method. What happens to the force of gravity if you double the mass of one object, but you also double the distance between them? Take a second. Think it through. So doubling the mass makes the force 2 times stronger, right? But doubling the distance makes it 4 times weaker. So you've got a 2 on top and a 4 on the bottom. That simplifies to 1/2. The new force is half as strong. And that brings us full circle, right back to the beginning with one last big, mind-bending question. From the third law, we know the pull between the Earth and Moon is equal. They pull on each other with the exact same force. So, why does the Moon orbit us? Why don't we orbit the Moon? Or why don't we both orbit some point in the middle? The answer, well, it pulls everything we just talked about together. The second law, F equals ma, is the key. So the crucial question is, how does an object's mass affect its acceleration when the force is the same? I'll let you chew on that one.